Okay, so this is my code to calculate the internal energy of a one-dimensional quantum gas at a particular temperature and for a particular size box and a particular mass of quantum mechanical particles. And all I'm using is NumPy and Matplotlib to do the calculation of the internal energy and the plot things relevant to calculating internal energy. So this second cell here, this is basically the parameters of the problem. So I need the temperature of the sample of gas. So that's defined in there, 295 Kelvin. I need the mass of the gas atoms. So this is the mass of the proton. I've forgotten what I picked now. I think it is. So it's like mass of hydrogen atom or something. And then this is the size of the box, tiny box, an angstrom-sized box. And so those are the kind of the parameters of the problem. There's one more parameter, which is the number of atoms. Because I wanted to rerun it with different atoms, I've not put that in that cell. There's a couple of constants of nature, right, that go into this calculation, Boltzmann constant and Planck's constant. So I also put those in there. So nothing unexpected there. So this cell here, which isn't that long, is where I do the entire calculation of this Markov Chain Monte Carlo method by generating sequences of random numbers to calculate the internal energy of the gas. So it just fits, neatly in one little cell. There's a couple of arrays that I've defined, one array and one list I've defined. So in this case here, I'm going to imagine 500 atoms in the gas. So that's the quantity n. I'm going to make an array that has that dimension. I called it microstate. And that array of dimension 500 will specify the individual microstate at that moment in the code. So for each element of the array, I'm going to store the principal quantum number. So if I store 500 principal quantum numbers, that is the microstate in my one-dimensional quantum gas. I'm going to initialize it to all be one. So I'm initializing it to this very first microstate is every atom of the 500 atoms is in its ground state. And so that's what I've done here with this array microstate. Okay, then I initialized a list. I did a list here because I think I wanted to keep appending to the list, but it could have been array. And I actually am going to fill the first entry in the list here. It's going to be the starting energy for my gas of 500 atoms. So if you look at this little equation here, it's n, the number of atoms I've got, times the ground state energy of these one-dimensional quantum mechanical atoms in a box. And so that's the initial energy. So that's all I've done there. Then I've got steps. So as I said, we're going to take a random walk, just like we took random walks in the last class. These are going to be a lot longer random walks. As you might imagine, perhaps, even, I don't know how many, in 100 coins, we had 10 to the 30 microstates. in 500, I have no idea how many. I mean, it's some enormous number of microstates. And so there's this enormous world of microstates, and I'm going to sort of start walking and gravitating around in it. And it typically takes, not tens of hundreds, thousands of steps in your random walk, but much larger than that to equilibrate, to gravitate to the average microstate. So I got 200,000 here. And then I just got a for loop through those 200,000 steps. In the for loop, I've got a couple of different calls to random numbers, and I've also got this accept decline logic, so whether if I'm going up in energy to accept or decline it. And then I've finally got the logic that updates the energy of the new microstate if I've accepted the transition to the new microstate. So firstly, this picks a random integer from 0 to n. And so this is just randomly picking which atom am I going to fiddle with. So I do that. And then, so that's one random number generator. Here's the second one. So in this one here, I'm going to pick a random number between 0 and 1. And if it's less than 0.5, I will increase the energy. And if it's more than 0.5, I will decrease the energy. So here, 50-50, I'm just throwing, here I'm throwing a coin, right? Whether I'm going to increase or decrease the energy. And then if I decide to increase the energy, so that's these two lines here. The principal quantum number for this atom is going to go up by 1, and the energy is going to go up by this factor here. So this again is that formula that I wrote down for the energy change when you raise the energy, and there was another one for the energy change when you decrease the energy. It needs the array microstate because that's storing the quantum numbers for the current state, the current microstate. So I need to get the current quantum number to calculate the energy change. And then there's the same thing. These two lines are exactly the same thing, but this is when I had the other choice. I decided to randomly to go down in energy. So now I've got I'm going to be decreasing the quantum number of the this particular atom by 1, and I'm going to be lowering its energy by this this negative amount here, which again just it needs to know the current microstate to calculate that. The current state of that atom, which is stored in the array microstate, to calculate that. So out of this section of the code, I come out of that with a basically a DN and a DE for my particular atom that I'm fiddling with, playing with. This next piece here, this logic here, these two if statements. These are the two statements that are going to enforce this acceptance or rejection of the transitions. So I said we accept all the downward transitions. We accept them all except if you try and go beyond or below the ground state. So that first if statement here, this guy is simply a protection against going below the ground state. So if the microstate if this number here, if the quantum number stored in the microstate is greater than 1, then you can always go down. So that's what, if this was 1, if we were in the ground state, we mustn't go down. So that's the protection against that. And then the second if statement, this is the one where I'm going to, in a probabilistic fashion, sort of accept or reject upward increases in energy based on the size of the energy. So that's where the Boltzmann factor is coming in. You've got the change in energy, dE, divided by kT. So if dE was large compared to kT, statistically, I would tend to reject it. If dE was small compared to kT, statistically, I would tend to keep it. Anyway, so out of these, if we're still inside this section of control here, after those two if statements, we are updating the microstate from the prior one to the new one. So at that point, I update the array. I update the array microstate that contains the quantum numbers of all the atoms, and I'm going to update I'm going to adjust the energy. So that's the energy of the macroscopic internal energy of the gas for that microscope, and that's what I did in these lines here. Is that okay? Might take pretty quick. Okay, so I've done that, and what I'm now going to do is just plot so I saved all the energies of all the microstates on my random walk through the atoms and the states of the atoms of the gas. So I've saved them all in this array E. And so I can just plot that array EI. I can just plot that versus the step, the 200,000 steps. And that's where you see what I kind of argued would happen, but now we're going to see it happen. So we started out with an internal energy down here. Everything was in the ground state. And then we started to randomly walk. And you see, initially, you're kind of burning this system in. You're raising its temperature because it's this cold gas in this reservoir at temperature T. So this is the burn-in period. It burnt in pretty quickly. And then you get into this period where you're sort of in equilibrium with the surrounding reservoir, basically. And, you know, it's varying statistically. But this here is where you're kind of sampling the average, the abundant microstates. And so that when it becomes this horizontal line, you can interpret that as the internal energy of the gas. Look, we know kind of the answer to this problem anyway, in a way. You've got N atoms in this gas, and they got, you know, this in one-dimensional box, sort of 1/2 N times KT is the scale of the internal energy of the gas. And so I also did just calculate that here. And so you see it's sort of order, more than of order, it's about this number here. It's actually not exact. I mean, I've done this a few times now. This always seems to give a little fraction higher. I don't know why that is. If you figure out why that is, let me know, because I'm puzzled by that. But anyway, this is, we've gone through this whole process of simulating the gas in the box. Any questions on that? I must admit, yeah.
Can you explain that one? From
This one?
No, I mean this if statement.
Which one?
Yeah, this one.
This pair
Yeah,
here?
the second one. Yeah.
Yeah, okay, so think of the first one. Here there's two conditions that, so if Bn is, if we're raising the energy, we're just going to go on. Or if we're in the first excited state or above, i.e. we're not in the ground state, we're going to go on. The only thing this line here rejects is you're in the ground state and you're trying to go down. So this is how we stop that. That's not allowed to happen. So that's how we do that. Then the second if statement is really that accept decline based on the Boltzmann factor. So I'm going to generate a probability, a random number from 0 to 1. That's what this call is. And if it's smaller than this, then that's my condition for accepting. And if it's bigger than this, that's my condition for declining. So that's kind of a key thing in this random walk, that I'm accepting or declining a step based on knowledge of the Boltzmann distribution. Based on knowledge of the Boltzmann factor. Yeah, so that's a good point. I can show you a couple of other little things about it. Well, are there any other questions before I? Let me just show you. So maybe these give you a little bit of a feeling for what's going on. Okay, so what did I just do here? I've just simply printed the that array that is the microstate. So, you know, here you see this is just one microstate out of, 10 to some enormous power, but it's a typical microstate. And so you sort of see the statistical distribution of the excited states of these 500 atoms. So they're all listed here. So that's kind of mildly interesting to see. I mean, look, there's one up here that's in the 9th excited state. There's a bunch that are still in the ground state, and that's the most likely state you'll find them in. And then the next most likely will be the first excited state. This plot here is just the plot of those numbers. So this is as 500 atoms and their particular states that they're in, particular principal quantum numbers. Here's this one that got to 10. But you see, there's a lot more in the ground state and low-lying excited states, which is what the Boltzmann factor does for you. This is actually a histogram of, I don't know if I actually, no, I didn't do it. So this is a histogram of these distributions. So this is the multiplicities of the different states up to 10. And so this is kind of just a projection of these, or a histogram of these numbers here.